that. Okay, so I'm going to talk about how we can see things that you can't actually see, and it's all about infrared light and infrared cameras. And so this is a picture of me with an infrared camera, but I'm going to talk about all the things that we need to know. I'm going to talk about light. I'm going to talk about how we see stuff. So let's start off with other examples of extraordinary vision, things that can see where you can't see. And so this is Superman. I don't know if you're familiar with Superman, but Superman has this thing called X-ray vision. And so we don't know how it works because it's just make believe, but there is real X-ray vision. In fact, this is an X-ray image of my own leg when I broke my leg 30 years ago, just as an example of something that you may have seen with X-ray vision. Then we have other types of extraordinary vision. This is the Mandalorian, and if you've seen that, he has this thermal imaging, and that's what we're going to talk about today. But I do want to show you a couple other examples of seeing things that we can't normally see. And here is this is Legolas. He is from Lord of the Rings, and he has visible light viewing, but he can also see extremely far, more than a normal human could. So that's another example. And he can kind of see in the dark too. And then finally, one of my favorites, this is a radio telescope. These look at radio waves, and we can use these for astronomy. They're super important. And in fact, they were the way that we could create this image, this new image of a black hole that we had never seen before. This is a radio image of a black hole, and that's not too terribly far away. And it's one of the first we've ever seen. So it's kind of exciting. I really like that. And it's something that you can't see with normal vision. So what is vision and visible light? If we think about electromagnetic radiation, it's a oscillating electric and magnetic field, and it has a very, very wide range of wavelengths. So it can be as large as 1,000 meters for a wavelength, down to wavelengths that are so tiny that they're hard to even describe. But in a very, very narrow range of wavelengths, from 750 nanometers to 400 nanometers, we call that the visible spectrum, and that's the region that our eyes can detect. And we interpret different wavelengths as different colors of light, and that's the visible spectrum. But there are other regions that we can detect with other detectors, such as the radio waves, infrared, and even ultraviolet and X-rays. So here are two visible light images. I took both of these. They're both from Louisiana, in case you want to see a picture. But the one on the left, we can see there is a street light, and that's what I want you to focus on. How do we see that street light? And the way we see that street light is different than the way we see the flower. But we can see both of them. And the key thing is, how do we see these things, and how does that have to relate to infrared images? So in order to see anything, we have to have light enter our eyes. And so in the case of a street light, the street light produces light, and that light enters our eye. In the case of an apple or a flower, we need a light source, and that light source has to reflect off of the object and then enter our eye. But without the light, we don't see anything. But the key thing is that light has to enter our eye, and that's how we see. Okay, so there are some things that are so hot that they glow. So this is, we don't really use these anymore, but these are incandescent light bulbs, and they produce light that we can see. You can see this filament in this light bulb. And the great thing about this is that that filament works by just getting so super hot that it produces light. And so really, really hot things produce light. And that's exactly how these old incandescent lights work. They're such a simple device, and that's what I love about them, but they're not super efficient because they produce a lot of thermal energy that we don't want, while also producing the visible light energy that we do want. So they're not great devices, but they're for energy, but they are good for physics and for explaining how things work. And so there's an example of how things get hot. And this is our connection here to how an infrared camera works. But there are other things that glow. that glow so hot that you can see them. So this is a picture of the element in my stove. So if you have an electric heater, it could be a toaster oven, it could be the element on a stove. It's really just a giant wire, and you run current through it. And when you run current through it, it gets hot, and that cooks your stuff. But at some point, it gets so hot that it glows, and it may look like this. So hopefully, you've probably seen this in one of these types of heaters. That wire is so hot that it glows. It's not as hot as the filament in a light bulb, and it doesn't glow as hot, but it is indeed glowing. But here's the magical part. It turns out that even in the image on the left, when you can't see any visible light from it, it still produces light. It just so happens that the visible light that produces is not the light that it produces is not in the visible range, it's in the infrared range. So if I had a special camera and I could look at that filament, in this case, it is on. This is what it looks like. So this is the same exact this is the same time as the picture on the left, but this is with an infrared camera. So in this case, that filament is producing light. I just can't see it with my eyes, but I can see it with an infrared camera. And so that's kind of magical. But let me show you one picture about how that works, and then we're going to look at some pictures and videos, examples of stuff you can see with an infrared camera, because it allows you to see stuff that you couldn't normally see. Okay, this is kind of a complicated graph, but this is a diagram of what we call black body radiation. So the idea of a black body is something that produces light only because of its temperature. So if this stove element is a good example of a black body because it's producing light from its temperature, not reflecting light from other things in the infrared region. Another example of a black body is the filament in the light bulb. That gets so hot that it glows, and it's mostly producing light because of its temperature. And then finally, another great black body example is the sun. The sun is, the surface of the sun is what we see, and it's so hot that it glows a particular color that we can see. So what this graph shows is that as you increase the temperature of an object, the wavelengths that it produces get shorter and shorter and shorter. And so at normal temperatures, the wavelengths this produce is not in the visible region, it's in the infrared region. And so you can't see it with the naked eye. But then as that element gets hotter, it does produce wavelengths in the more visible range. It starts off getting red, and then it moves it to shorter and shorter wavelengths, but it combines those. So a very hot thing would be red, but a super, super, super hot thing would look bluish white, okay, because it's more in the shorter wavelengths. Okay, so now let's look at some infrared. Oh, this is one more picture I forgot. So who discovered this whole idea of infrared, and why is it called infrared? So this guy in 1800 was studying the effect of different colors of light on temperature. So what he did was he took a glass prism and he took light from a source and made this rainbow of colors. If you shine it through this prism, then different colors bend different amounts, and you can separate it out. And then he took thermometers at different places in the rainbow of colors to see how each color would affect the thermometer. What he found was that even when he put a thermometer beyond where the red color was, it still got warm. So that's really what that infrared means. It means past red. And he found that there is another spectrum of light beyond red. We just can't see with our eyes, but it still does stuff, and they associate it with temperature. So here's two pictures. That's both me. On the left is, these are two infrared cameras. And the great thing that I love about infrared cameras is that they are, for the most part, affordable now. The one on the left is a camera that actually attaches to your phone to allow you to see things in infrared. And that's the one I usually use. I talked to the people that make this camera, and they let me borrow the one on the right, which takes much higher resolution images, but no one would ever buy it because it's so expensive, and you couldn't. It's not affordable in the least, but it's fun to play with. So I played with that camera for a while. The one on the right, it's much more expensive, but you can get great images with the one on the left too. Just 10 years ago, even a normal basic infrared camera would be really unaffordable for using just for fun. So those are two cameras, but you can find a lot of ones like that. They're really inexpensive. In the past 10 years, the price has gone down. So okay, now there's this is an infrared picture. There's a lot to see here. Okay, but I really want to talk about the colors in this picture. This is a picture of my power adapter for my computer, and when you plug it in, you can't normally see if it's plugged in or not with the visible light, but with infrared, I can see that it's hot. But I want to focus on the colors because these are not real colors. What we can't see infrared. So what the camera does is it makes a translation between different wavelengths of infrared light, and it converts them to a particular color on the computer or the screen so that you can see. In this case, there's a temperature scale. This is a palette that goes from purple colors are being colder and yellow are warmer. And the range of the scale you can set to match your picture. And I could actually change these to see different things. But for this case, and I apologize, I left this in Fahrenheit and not Celsius, but you can see that the colder stuff is purple, the yellow stuff is warmer, and so that power adapter, even the cable coming out of that is warm. You can actually see the warm cables in the infrared. And this could be in a completely dark room, but it doesn't matter because these are producing their own light. So this false color idea is important. Now let me show you two examples of the same picture with different color palettes. Okay, so this is actually my dog. And it's the same picture, but the one on the left is in a black and white pattern. So in this version, the whiter colors are brighter and the darker colors are dark. And you can see his eyes and his nose are actually warmer than the rest of his body because he has this fur that acts as an insulation, so you can't really see his temperature. Now on the right, it's the normal. This is called I think it's called iron, the iron palette, because it uses purple for dark and then yellow for bright. Now I do want to point out something else. He's laying down on a floor, and it's a smooth floor, and you can actually see his reflection on the floor in infrared, but you can't see that in the visible light. So that's one of the great things about infrared light is that it interacts differently with matter than visible light does. So things that would not be shiny in the visible spectrum are actually quote shiny in the infrared. And this is a great example of why I love this, because you can see things that you couldn't normally see. You can look at a whole bunch of stuff in this image. One of the things is this warmer region on the floor to his left. And it's warmer there because he was laying there. He was laying there and it warmed up the floor, and you can see that. You can see that in the camera, and I find that magical. Now, there is one problem with converting these colors into temperature. So what you see is not always what the temperature is. These are two aluminum cans at the same temperature. But the difference is the one on the right has tape around it, and the other one has nothing on it. And aluminum is very shiny, not just in visible light, but it's also shiny in the infrared. So the light I see coming off of the can on the left has a lot to do with reflecting light around it, whereas the one on the right with the tape actually it is more, I'm seeing its temperature. So the one on the right looks darker because it actually is cold. They're the same temperature. You can see the reflection of my hand in the can on the left. So this is called emissivity. And if you want to use infrared light to measure temperatures of things, it's something that you'd have to take into account. Because if I just look at the color of those, I'm going to get the wrong temperature on the one on the left. And we use these cameras or things very much like it a lot of times now to measure your body temperature to see if you're sick. It's the same idea. So sometimes the human skin is actually not as reflective, so it actually works very well. But if you were an aluminum can, it wouldn't work so well. But good thing we're not aluminum cans, so that's good. Okay, I like this picture. This is a coffee. You can, again, see so many things in this picture that you can't normally see. As I pour the coffee into the 2 coffee cups, the cups get warmer. And they get warmer from the bottom because that's where the coffee hit first. And you can see how much coffee is in the cup. These are not see-through cups. These are just your normal ceramic coffee cups. You can also see how hot the coffee pot gets. And you can see reflections of the coffee cups on the counter too, which again is not shiny in the visible region. Everything else behind is mostly the same temperature. So you can't really see a lot of that. We're seeing things at different temperature, but infrared light does reflect off of those, and we can see it just like you would in the normal sense. This is a student at our university, and he's wearing a face mask, and he's breathing. And you'll notice that the color of his face mask changes as he breathes. And that's because when he exhales, there's moisture in his breath, and it gets the mask wet. When he inhales, that moisture evaporates and it cools off the mask. And so the mask gets colder and darker. And so you can see on their shirts, places where it's wetter from sweat or whatever are darker colors. This is a picture of the back of my house in the summer. There's a couple things you can notice here. One is the roof of my house is very hot. You know, it's in Louisiana, so it can get very hot in the summer. The windows are not very hot, and the reason there's especially around the windows, because the inside of the house has an air conditioner and it cools off the house. You don't want these windows to be cold, because that means that you're losing energy to the outside. But windows are typically a place where you do lose energy around there. Now, there's another thing that I really like, and I didn't even notice until I got this image. If you look near the middle of the screen, there are 2 very, very dark objects. Those are 2 cold drinks sitting on a small table. You can actually see that from far away because they're so cold, and they show up on the warmer background. And I think that's really cool. Okay, I love this picture. This is actually outside of my house, but this is a ceiling fan. And one of the great things about the ceiling fan is you see it's running, and the base of the ceiling fan is very bright yellow because it's hot. So ceiling fans get hot. And a lot of people think, oh, well, fans cool you off. And that is true. Fans do cool off humans, but they don't cool off anything else, okay? Unless they're super, super hot. So what a fan does is it takes air and it pushes it. And for humans, that works very well because that moving air helps the sweat on your skin to evaporate faster. And as you saw with the face mask, when the water evaporates, it cools off. So that's how humans get cooled off. They cool off through evaporation of our sweat. And so the moving air helps that. If I have an object of a normal temperature, the moving air over it doesn't actually cool it off at all. It just doesn't do anything. So humans really like fans, but nothing else does. But the fan actually technically gets hotter than the surroundings because it has an electric motor in there with current running through it. So this is a picture of me taking a picture of my window. And there's something very important here in that you can see me, but you can't see into the house. You see out of the house. So infrared light doesn't go through your glass windows. The glass windows acts like a mirror in infrared. So you can't see through that. And that is really important too. Different wavelengths of light interact differently with matter. Visible light goes through glass, infrared doesn't, but things like radio waves can go through the walls. That's why your cell phones and your Wi-Fi goes through walls, because that's a radio wave, but visible light does not. So we have all these different properties of electromagnetic waves and how they interact with matter. And this is a great example of that. This is a picture of my sofa in one of my rooms in the house. And if you think about this, it looks really weird. And it looks weird because one of my children, he's old, he's a big child, was sitting on the couch, and then he left. And so you can see where he was sitting because he is warmer than the couch, and he warms up the parts of the couch. And when he gets up, those parts of the couch are still warm. So it kind of looks like a ghost, but it's not. Just that's where he was sitting. You can see even on the side where he had his arm. He had his arm on the couch, and that part's warm too. You can actually kind of see his leg and everything if you look. And I think that's amazing. So he's not even in the room, but I can still tell where he was sitting. Okay, so I think I'm going to stop there. I'm not sure about the time and stuff, but here's a picture of me with the camera wearing a mask. You can also notice I have glasses, and you can't see through the glasses because it's an infrared. But I'm going to we can talk about any infrared questions that you have, or any other science questions that you have. I'm happy to answer anything that I know stuff about. But well, let me stop there and get out of the presentation.
Rhett, thank you so much. Can we very quickly? We've got time for about a couple of questions. So over to you guys. Yes, please. What's your in the corner? Sorry, what's your question?
I'm from
Oh, sorry.
Are there any animals that do see an infrared?
Are there any animals that do see an infrared?
Yeah, actually, humans can see an infrared, but they can see only in the infrared spectrum that's very, very close to the red light. But we don't notice that because it's all blocked out by the visible light. Some people have made these special glasses that block out just visible light, and you can see very, 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 very near infrared. It's not the same as seeing things that are giving off heat, though, but it is possible. And so no animals actually see the far infrared thermal like that way I showed.
Any next question, please? Yes, please. Sorry, you had your hand up. Yeah. Okay. Yeah.
So about infrared. No, that's fine. So about the jumping at the same time, what would actually happen in something? Would nothing happen because there's not enough people and there's not enough mass? Or would it be like enough mass would cause enough earthquake or something?
Could you hear that, Rhett?
No, I can't hear that.
It's come back to what would happen if everyone jumped. Would there be enough mass to make an earthquake?
No, maybe. I mean, if everybody jumped, it would definitely shake the ground. I mean, it would be so difficult to get everyone to jump at the exact same time. But the mass of humans, even though let's say we have 7-8 billion humans on the planet, that mass is tiny and insignificant compared to the mass of the Earth. So it's a lot of people, but compared to the earthly-like things, is not very much. It would definitely move the ground a little bit. You can hear the ground move when a train comes by, so a little bit, but it wouldn't really cause an earthquake.
Fantastic question over there, please.
So do cold-blooded animals show up on infrared?
Do cold-blooded animals show up on infrared?
Yeah, they do, because it not as well as a warm-blooded, because they're most of the same temperature as the things around them, but there's still infrared light that reflects off of them, so you can still see them, but just not as well as a warm-blooded animal. That's a great question.
At the back, please. Yeah.
If you put an infrared camera to the ground, would you see like all the animals burying under the ground?
Could you see animals under the ground if you put an infrared camera onto the ground? Would you see worms or that sort of thing?
Not unless they're very, very close to the surface and very warm. The dirt does, you can't see through the dirt with infrared, but if they're very large, they would warm up the dirt and you can see where they are. So some of these small animals that burrow in the ground, if they're stationary for a long time, they would warm up the dirt around them and you could see that. But so normally you can't see things. You can see ant beds. Ant beds show up because they're a different temperature of the ground than normal grass because they reflect light differently, and the activity of the ants does warm up. So you can actually see that.
Yes, please, that question.
other types of cameras that can see other types of light.
Other types of cameras that can see other types of light.
Oh, absolutely. We have, especially in astronomy, we have radio telescopes. You've seen X-rays. That's another type of camera that can see other types of light. We have ultraviolet cameras, and in fact, normal cameras can see ultraviolet light if you block out the visible light. But we also have ultraviolet telescopes that we put in space to look at different galaxies that give off ultraviolet light, and we can see different things about those than we could with visible light. But the ultraviolet telescopes have to be in space because that light doesn't go through the atmosphere very well.
Thank you. We've had, I'm sorry, we have the bell's about to go. We've had an absolutely fantastic time. We're going to see the world. We're not going to see the world differently, but we're going to understand that the world is different as a result of hearing your talk. So thank you very, very much. Can we give a big round of applause, please? Thank you. Have a good night's sleep and a good day tomorrow. Thank you so much for joining us.
All right. Thank you too. Okay.
Thanks very much.
Bye.
Thank you. Thanks. Bye.